In our last video, we looked at some ordered pairs and talked about the concepts of relations and functions and graphing functions. But in this video, we're going to look at some more interesting functions, and we're going to see that this is going to be more relevant to what we will need to do moving through the semester. If I have a function, actually, you know what? Let's say I have a relation. I don't know for sure if it is a function or not. So let's say that I have x squared plus x squared minus y equals 3. Now, this is a relationship between x and y. It gives me a mathematical connection between values of x and values of y that make this a true statement. If I can get y all by itself, in other words, isolate y, so I would add y to both sides and get y over here on the right and subtract 3 from both sides and get x squared minus 3, I can get y all by itself here. Y equals x squared minus 3. So this is another way of writing this same relation. It's the exact same equation, so it gives me the exact same relationship between my values of x and my values of y. If I know that for any single value of x that I plug in, my output is going to be a single answer, a single y, then I know that this is a function. So let's just create a t-table here. Later in the semester, we're going to learn how to graph this relation, and we are going to see that this is a function. But we're going to learn how to graph this in a much quicker, easier fashion. But for now, we're just going to plot points. This is called a t-table because I can choose values of x and then plug them in and see what y is equal to. So if I let x equal 1, I can plug in and I can see that I have 1 squared minus 3. So y is equal to 1 minus 3, which is negative 2. So when x is equal to 1, y is equal to negative 2, and I get 1, negative 2. That's the same thing as the ordered pair 1, negative 2 on a coordinate system. So let's go ahead and plot that ordered pair 1, negative 2. It's usually best when graphing if your hash marks are fairly equivalent. So what I'd like you to do, I'm going to just go ahead and give you some other values of x, and I want you to figure out the y that goes with each of those, write an ordered pair, and plot those ordered pairs. And go ahead and do each of those. Plot them on the coordinate system. Pause the video, find each of your ordered pairs, plot them on the coordinate system, and then start the video back up. All right, so if we plug in negative 1, we get negative 1 squared is 1, minus 3 is negative 2. 0 minus 3 is negative 3. 2 squared is 4, minus 3 is 1. Negative 2 squared is 4, minus 3 is 1. So I plot each of those ordered pairs. And if I were to continue to plot ordered pairs, for instance, if I plotted x equals 1/2, or x equals 7, or x equals negative 3/2. I could keep plugging those values of x in, and I could keep finding more and more and more points, and I could fill this whole graph in, and I see that I get a nice shape like this, and that is called a parabola. And we're going to learn, as I said earlier, we're going to learn more about relations or functions that look like this and their shapes in a later lesson. But for now, we're just saying what it would be like with plotting it with the t-table. So if I asked you, is this a function or not a function? We see that it is a function because it passes the vertical line test. Anywhere I draw a vertical line through it, I only touch it at a single point. So this is a function. That means that I can write this using what's called function notation. So if I have my relation y equals x squared minus 3, and I know that it's a function, I can replace the y, my output, with f of x equals x squared minus 3. So y and f of x are the same thing. F of x means, if I'm looking at my function f, and I start with the value x, what does it plot to? And that would be my value y. So I can use function notation to find the function value of many different numbers. For instance, f of 5. That means put a 5 where the x was and evaluate. So when x is 5, y is 22. So that means that a point on my graph is 5, 22. So the function value, f of 5 equals 22, is the exact same thing as the ordered pair 5, 22. And if I were to plot that on my graph here, there we go. And then I'd come way up here to say 22 on my graph. 1, 2, 3, 4, 5. That would be another point on my graph. So that tells me my arrow keeps going. So all of these infinitely many ordered pairs that I'm creating here, say f of negative 3, f of 1/2, f of 7, I can find each of those function values, and it would create a point somewhere on this graph. So these infinitely many ordered pairs is exactly the same thing as all of the values of x and the y's that they map to. So looking at it the other way, if I found a point on the graph, that would mean that those numbers, the numbers that I had plugged in there for x and y, make this a true statement. So if I asked you, is the point 3, 6 a point on the graph, is 3, 6 a point on the graph? What you would be doing is saying, is the point 3, 6 a solution of this function? Does it make it a true statement? The 6 is the f of x, the y. The 3 is the x. So I see that I have 6. We're seeing if 6 is equal to 9 minus 3. 6 does equal 6. So yes, 3, 6 is a point on the graph of f of x equals x squared minus 3. Now, let's look back at my function here. Let's look back at the concept of domain and range. I can see the domain and the range from this picture. The domain is all the values of x. So I'm going to sweep across. I'm going to visually look across from left to right because that's the x-axis. If I'm sweeping across from left to right, and if I had a pencil, I could draw a vertical line with my pencil, sweeping across. And I see that I am touching the graph somewhere. I'm touching the graph everywhere. And because this keeps going up forever, as I come out this direction, I am still touching the graph. So that tells me that my domain is all real numbers. And I'm going to use something called interval notation. And that just tells me the interval of my domain. And I always write my far left number, then a comma, then my far right number. And because this goes forever to the left and to the right, I have negative infinity, but I can't ever reach negative infinity, so I use a parenthesis. And then it goes forever to the right, so I use infinity. I can't ever actually reach infinity, so I use a parenthesis. Let's look at the range. If I look at the range on this, the range is the values of y. So as I'm going, you know what, I'm just gonna come down here and redraw this graph. I'm getting kind of a messy graph there. Let me go ahead and redraw this. I've got f of x equals x squared minus 3. And I plotted points to see what my graph looked like. Can't remember what that one was. Yeah, 1, negative 2. And I could have just mentally plugged it back in. But anyway, so my graph looks something like this. And we saw that we swept from left to right to see where we're touching the graph, what values of x, for the values of x that we were touching the graph. And for the range, we are going to start from negative infinity on y. This number line is my y-axis. It is a number line. It's going to infinity up here and negative infinity down here. So as I'm sweeping up from left to sweeping upwards and saying, where am I touching the graph? I see that if I'm down here, I'm not touching the graph at all. The very first place I start touching the graph is right here when when y is negative 3. And then I continue to touch the graph forever to infinity. So that tells me that my range starts at negative 3. And notice I used a bracket here because that means I'm including negative 3. And then continuing on to infinity. Can't reach infinity, so I use a parenthesis. So that is the domain and the range of this function. In our next video, we're going to look at some other concepts on functions, some terminology of constant, increasing, and decreasing. And we are also going to continue to practice finding domains and ranges by looking at graphs.